We will get started with the final session, which is on heterogeneity and aggregate fluctuations, insights from tank models by Davide Debortoli and Jordi Gali, and Jordi will present.
Very good. Thanks so much for putting the paper on the program. The joint work with Davide that will answer all the hard questions later. So for decades, macroeconomists have been developing, teaching business cycle models that relied on the assumption of an infinitely lived representative household. And underlying that practice, there was a view that was widespread, I would say, that heterogeneity was not an important factor in explaining economic fluctuations. Now, this view has been challenged in recent years by the Hank literature, which has turned the spotlight on household heterogeneity in the form of idiosyncratic income shocks. Those shocks are embedded in this literature, in the typical Hank model, into a otherwise standard New Keynesian model. Now, the presence of these idiosyncratic income shocks and a lack of complete markets imply that the distribution of wealth is an additional state variable, which raises the complexity of the models substantially. Means that numerical methods have to be used in order to solve for the equilibrium, and the models become a bit black box in the sense that there is no simple intuition that one can gather from some of the simulations or predictions. So in this paper, we asked two questions. First, is heterogeneity important for understanding aggregate fluctuations? And second, if so, can simple tractable models approximate well the key properties of Hank models in terms of aggregate predictions and transmission channels? So what we do in order to answer that question is to analyze the aggregate properties of several Hank models. And we do so focusing on the distinction between unconstrained and constrained or hand-to-mouth households, which is the hallmark, the distinction of the so-called two-agent New Keynesian models, tank models, that justifies the title of our paper. So to be precise, we analyzed three versions of a Hank model, which we call Hank 1, Hank 2, and Hank 3. Hank 1 is the simplest version in a sense. There are no binding borrowing constraints, stocks are illiquid, and following much of the literature, profits are allocated to different households following some rule. Hank 2 is similar to Hank 1, but now we tighten the borrowing constraint, so it becomes binding for any household at any point in time, occasionally. And Hank 3 is similar to Hank 2, but we replace the assumption of illiquid stocks by allowing for an optimal portfolio choice problem. Now, for each Hank model, we propose a tractable counterpart that we draw from the Hank family and assess its merits as an approximation to the corresponding Hank model. And our focus in the paper is on monetary policy and technology shocks, even though we have some preliminary results also for fiscal policy shocks. So here's a preview of the findings in the form of answers to the two questions. Is heterogeneity important for understanding aggregate fluctuations? Potentially, yes, but possibly less than you may have thought, and in any event, not independently of the monetary policy rule in place. Can a simple tractable model approximate well the aggregate properties of a Hank model? Yes, but it must be properly designed and calibrated, and in particular, a typical tank model will not generally do the job. So here are the common elements in all our Hank models. And there's a continuum of infinitely lived households indexed by J that have a standard utility function, the one you see here, the sequence of budget constraints. They have access to a one-period riskless real bond that pays an interest rate R. And here this CTJ is it's the most distinctive feature of these Hank models. This is the idiosyncratic income shock. Okay, it has a mean of 1, but it's independently distributed across households. FTJ is the addition to cash on hand associated with equity holdings. So it could represent dividends or it could represent sales of stocks, depending on the model. And then we have a borrowing constraint that is standard. Then on the firm side, that's completely standard. We have it's taken off the shelf from the new Keynesian model. We have monopolistic competition, quadratic price adjustment cost, and combined with some auxiliary assumptions, this yields a new Keynesian Phillips curve of the sort that we saw in the previous paper. So inflation is driven by deviations of output from a natural level of output, and the natural level of output is proportional to the technology shock, AT. So an important feature is that the supply block is invariant to a heterogeneity. So that's important because any influence of heterogeneity in our model will have to come through the demand side, okay? Obviously, we think that it would be interesting in future work to also explore the role that the supply side could have. Monetary policy, very simple. In our baseline specification, we assume that the real interest rate is exogenous. We relax that later on. So let me turn to the specific model. So in Hank 1, we assume a natural borrowing limit, which means that in equilibrium, the borrowing constraint will not be binding for any agent in any period, okay? And then we assume that stocks are liquid and the profits are allocated to the rule that you see here on the screen, where this theta Tj is the fraction of dividends that accrue to household J in period T, and that is potentially a function of productivity, again, following some of the Hank literature. For all T and J, then a standard Euler equation for consumption must hold at the individual level. And we show that this Euler equation can be approximated and then aggregated to yield a log linear Euler equation for aggregate consumption that you see here, which looks like a standard Euler equation, except for this additional term, Vt, which we refer to as a risk shifter, which is related to precautionary savings. And this risk shifter is a consumption-weighted average of the VTJs. And the VTJs are a measure of individual consumption risk. To be precise, the conditional variance of one period ahead consumption, individual consumption. Now, what is the tractable counterpart that we want to match this Hank 1 model to? Rank, the representative agent New Keynesian model. So in that model, as we all know, the consumption Euler equation can be written down like this. So we don't have a risk shifter in that model because by construction, that risk shifter would be related to conditional variance of aggregate consumption is second order relative to variations in aggregate consumption and the real interest rate. This is not true in the case of the Hank model, because individual consumption, the conditional variance of individual consumption may be of the same order of magnitude as aggregate consumption due to the presence of idiosyncratic income shocks that obviously are not part of rank. So if you compare the two equations, you can see that heterogeneity in this Hank 1 model will have an influence on aggregate consumption and aggregate output only to the extent that it can affect this risk shifter term. Okay, so let's see if that's the case in a significant way, and we do so by we calibrate the model. Again, I don't have time to discuss the calibration, but we essentially rely on it on other people's works. And we look at some of its predictions. So here you see the impulse responses to a monetary policy shock and to a technology shock, again, under an exogenous real interest rate rule. So in red, you have the monetary policy shock. It's a persistent decrease in the real interest rate, and you see that consumption and output expand. In red, you have the prediction of Hank 1 model, in blue of the rank model. So the two are very similar, okay, both in terms of the size of the impact and the persistence. The same is true for technology shock. In the case of rank, output remains unchanged because the real interest rate doesn't change. Okay, in the case of Hank 1, output increases, but just a little bit. And in the paper, we discuss in detail what are the mechanisms for these small differences. So here is a simulation of the path of output, aggregate output, in the two models in response to a sequence of monetary policy shocks. And you can see that the correlation is very high, very close to 1. So from this comparison, we conclude that there is a small impact of heterogeneity in this particular model, Hank 1, without binding borrowing constraints. So, and the intuition for this can be summarized simply as follows. Again, here heterogeneity should work through through its impact on the risk shifter. Okay, that is through the impact on consumption risk. Now, for rich households, consumption risk varies little in response to shocks. For poor households who are closer to the borrowing constraint, aggregate shocks may lead to variations in their wealth that may imply larger changes in their consumption risk. However, those poor households have low consumption by definition, or almost by definition, which means that their aggregate impact is small. In particular, the impact on the aggregate risk shifter is very small, thus the small aggregate implications. So we conclude that idiosyncratic income risk by itself doesn't have much, much of a role. And then, of course, we ask the question, does it have a larger role in the presence of occasionally binding borrowing constraints? And in fact, most Hank models have those binding borrowing constraints, and they emphasize their role. So that leads us to Hank 2. So now we tighten the borrowing limit. So we impose a borrowing limit that is a multiple of a steady state output, and is such that, this constraint will be binding for a fraction of households every period, a time varying fraction of households. So in any given period, we have two subsets of households, unconstrained and constrained or hand-to-mouth. Unconstrained households will satisfy the Euler equation, and we can again approximate and aggregate this Euler equation for those households, the unconstrained, and obtain a log linearized Euler equation for the average consumption of those households that looks like this. It looks very much like the one I showed you earlier. Now there is an additional term here that plays a very small role and has to do with the fact that there are some agents that switch from being constrained to unconstrained. Okay. Now, hand-to-mouth households, on the other hand, their consumption, we can write an expression for their consumption based on the budget constraint. So their consumption will be given by their labor income, their dividend income, the service of the debt they took on the previous period, plus new borrowings, which by definition will be the borrowing limit, okay, because they are constrained. Okay. Now we can average this expression for consumption for across hand-to-mouth households and obtain an expression that looks like this, where we also have made use of the equilibrium relationship between labor income, dividends, and aggregate output and the markup. Okay. So, and where this variable omega ht minus 1 represents the average debt in the previous period of these currently constrained households as a fraction of the debt, the borrowing limit. So this, in our simulations, we check that it's very close to 1. And intuitively, those who are constrained today were either constrained in the previous period or were very close to being constrained. So this is going to be very close to 1. Now there are two channels here that appear clearly that are absent in the rank model. The interest rate exposure channel, whereby changes in interest rates change the cash on hand of indebted households, and that affect their consumption and hence aggregate output, and the income distribution channel, whereby a change in the markup for any given level of output, aggregate output, changes the income accruing to those households. Now in equilibrium, the productivity of constrained households will be less than average, typically, which means that this theta t, okay, will be larger than the labor productivity parameter. Okay, these are averages across all households. Okay, which means that an increase in the markup will tend to increase the resources for any given level of aggregate output, increase the resources of the constrained households, and thus increase their consumption. Okay, so what do we take as a tractable counterpart to Hank 2? Well, what we call Tank 2, a modified version of the standard Tank model. So now we will have a constant measure of identical unconstrained households, which will satisfy this Euler equation, and then a constant measure lambda h of identical hand-to-mouth households for whom consumption will be given by their labor income, a fraction of the aggregate dividend income, and some interest, net interest payments on that. So what we're assuming is that these constraints, hand-to-mouth households are always against their borrowing constraints, so they will be subject to an interest rate exposure channel. And we're also, in contrast with the standard tank model, we're allowing their productivity to be, on average, different from the average household, and also to draw some dividends. So aggregate consumption we can obtain by just adding the consumption of hand-to-mouth and unconstrained households, and we obtain an expression like this. Now, we can compare here, you have the expression for aggregate consumption from the tank-2 model, aggregate consumption from the Hank-2 model, and if you're sitting, in the back of the room, you probably cannot see the difference. Now, if you zoom in, you will see that the only difference is that some of these Greek letters have a T subscript in one and not in the other. And the fact that here we have an omega, T minus 1, but I argued earlier that this is likely to be close to 1, okay, and we have a 1 on top, okay? So the tank-2 model will be a good approximation if there is not much of a variation in all these Greek letters. Okay, so let's look at we calibrate the model so that in the tank model, all the fraction of hand-to-mouth agents and so on corresponds to their hand counterpart in the stochastic steady state, and we proceed to do some simulations. And here you have impulse responses to the two shocks. Again, the tank-2 model captures qualitatively and quantitatively pretty well the predictions of the Hank-1 model, and here you have simulations in response to a sequence of shocks. And again, the correlation between the predictions of the two models is 0.99, so very high. Okay, why wouldn't the standard tank model work? Because in the standard tank model, we don't have there is no interest rate exposure, and it turns out that the income distribution channel has the wrong sign, the response to changes in the markup. So here you see in green the predictions of the standard tank model, which are completely off. In particular, in response to a technology shock, there is a decline in output because the increase in the markup reduces labor income, and that reduces consumption and output. Okay. Now, very briefly, Hank-3. In Hank-3, we allow for an optimal portfolio choice. Okay, so there is households may hold also equity and can sell it, but it is subject to some adjustment costs. So in this economy, there are two types of households, two types of hand-to-mouth households: poor hand-to-mouth and wealthy hand-to-mouth. Okay, the poor hand-to-mouth are against the borrowing constraint in terms of debt and hold no equity. The wealthy hand-to-mouth are also against the borrowing constraint, but hold some positive equity which they can use to smooth consumption, but at a cost. So they are semi-hand-to-mouth, let's say, okay? And, well, our tractable counterpart is what we call Tank-3, in which we also allow for two types of hand-to-mouth agents, okay? Poor hand-to-mouth with a constant fraction that are always against the borrowing constraint, like in Tank-2, but you get no dividends in this case, and the wealthy hand-to-mouth that are always against the borrowing constraint, the binding borrowing constraint, but now they yield some dividends. And again, here are the impulse responses, very similar in the case of monetary policy shocks. In the case of technology shocks, there is more of a gap. But notice that qualitatively, both the tank model can capture the fact that under the assumed policy, under the assumed constant real interest rate, output decreases in response to a positive technology shock here. Okay, so in the final part of the paper, we endogenize the monetary policy, and instead of assuming a constant real interest rate, we assume a standard Taylor rule, and also we introduce nominal bonds. Okay, so here the results are, we were really surprised about this. They're quite striking. So here you have the impulse responses implied by the 6 models that we consider, and they lie on top of each other. Okay, they are very, very similar. So. And here are the simulations of artificial time series, okay? They are on top of each other. So we were surprised about this, but then, of course, we thought about this, and this is not that surprising. The intuition is straightforward if you think in terms of the New Keynesian Phillips curve, okay? The Taylor rule tends to stabilize inflation, okay? Which means that it tends to stabilize also the output gap, with a divine coincidence, which is embedded in the New Keynesian Phillips curve. Now, the natural level of output is invariant to heterogeneity. But if the output gap is stabilized, that means that output gets closer to the natural level of output, and hence output will be similar across models independently of the assumptions that they make about heterogeneity. In fact, we take it to the limit in a proposition which takes a very simple form. Under a strict inflation targeting policy, there is, if inflation is zero for all periods, equilibrium output is invariant to the presence of heterogeneity because the output gap is closed, output equals to the natural level of output, and that is independent of the presence of heterogeneity. So to conclude, idiosyncratic income risk is a key source of complexity in Hank models, but it seems to have a relatively small role in aggregate fluctuations. The aggregate predictions of Hank models can be approximated by a suitably calibrated Hank model, qualitatively and often quantitatively, and more so if monetary policy is one that focuses on inflation stabilization. Now, we think that Hank models are, we are fans of Hank models and of the Hank literature, I have to say, and they are potentially useful for many purposes, including looking at the distributional impact of aggregate shocks, the role of inequality in the optimal design of the optimal monetary policy design. Now, in future research, what we plan to address is whether Hank models, simple tractable Hank models, can also approximate Hank models predictions on those dimensions. Thank you.